Hi there. Wow, there are a lot of people here. I'm happy to see all of you on this webinar. Long time no talk, huh? And finally we are together. So the topic of our webinar today is the Visual NAND Reconstructor version 11. Within many years, Rusolut changes their business of chip-off data recovery and digital forensics. Some time ago, we implemented ECC correction on GPU. Then we did AI XORs, which allowed to create XORs right on the patient drive without any donors. And for modern devices, it's very important because with some controllers, each and every device have different XORs, little bit different XORs. So you cannot just create it from the donor device. You have to generate it from the patient drive. Later, it was a file assembler, then vehicle data reconstructor. And today, we implemented new huge improvement, massive improvement to the industry. We made the algorithm which allows to search for read-retry parameters to fine-tune the reading process without ECC. So it means that right in the moment when you begin the case and you have no idea about the ECC which will be used there, about anything, about controller actually, based only on the raw data which you have in the memory chip, Visual NAND Reconstructor can adjust the reading parameters, and then from the very beginning you will get much better image. I mean, the initial image will be much better than you would get with default reading. That's the main topic of Visual NAND Reconstructor version 11. But first, I think let me say several words about other topics also of the update. So here we have the eMMC NAND Reconstructor improvements. Within many years, this wizard was not updated, and finally it was refined, it was updated, and now it's much more convenient to use it. It's much more convenient to read the chips, to run correction on the chips. Also, you can see the ECC map right on the wizard. So you can kind of understand, you can control if the image is good, if you read data with a good quality, or if something is not right, let's say. So the eMMC NAND Reconstructor wizard was improved. NAND chips were, the configurations for newer NAND chips have been added. Same for XOR keys, ECC, but the main improvement, of course, is the fine-tuning, adjusting for memory chip reading. And basically what? I guess I can just go to some cases and I will show you how it actually works. So first let me run the VNR here. Now you're supposed to see a Visual NAND Reconstructor screen. Do you see that? All right, great. I'm going to show you how to use that new mode, that adjustment, and how it works and how it basically improves the quality. All right, so let me create the new case. Let's call it case number 1. And here. Okay, so now the database is updating from the cloud. Yeah, that's another improvement we did to the VNR several years ago. It has the online database, but with the local version. I mean, it's local, but dynamically updated from the cloud. And for now, I have SD card. For the first case, I have SD card, so I need to select this type of device. Let me remind you that when you create the task, it's better to select the device and type of device and controller because VNR has the database of solutions, and if your device was time ago analyzed by us, if somebody else added solution to the database, you will get it ready right on your workspace. My first device is SD card. Here we can set the capacity. It's 8 GB as far as I remember. However, the capacity is not that critical. The important thing is to select the controller correctly. We need to correctly select the controller. So here we have the list of all the controllers, right? We can filter it by the vendor, and it might help you just to narrow the list. But in my case, I have the device with a black blob, so I cannot read the controller name. So what I need to do, I need to select the black blob here in this list. And now I see the SD cards with black blobs, which we have solutions for in our database. And it may not be that convenient to search the device because there are quite a lot here. However, anyways, it's better than just to search for the solution, to do the solution by your own. So in my case, I have the card which looks like this. We can do a double click, so it will be enlarged, and we can just compare this. Yeah, that's the card. You can ensure that that's the card you are dealing with in that moment. So once the card is selected, we click to the finish. And the first step would be to read the memory chips. So as usually, I go to the configuration selection. So I click to set configuration. Okay. Now VNR tries to read the ID. That's the ID of the memory, which belongs to that SD card. And there is only one configuration. I can just apply it. After that, as we suggest, it's better to check the reading quality. If we see here more or less normal looking data, normal looking patterns, then we are good to go further. All right. So after that, I just go to read memory chips. So that's not necessary to run any additional tools. We try to do this as straightforward as possible. So I click to read memory chips. Here I need to select the number of chips. As you remember, in our case, it was number 2. And okay. And due that we selected the black blob, the device, VNR understands that the RIOS device is actually equal matches to the device from database, so it offers you to apply the solution. You click to apply, and here you get the solution for the device. After that, just in case it says you that you need to insert the chip, you say okay, And in this moment, the new tool begins to work. Let's discuss this window more detailed. First of all, when you just run the reading, let me run it again, and pay attention. Now it's saying for the reading dump from the reader. In fact, it's not reading the dump in that moment. It's just searching for the good block for analysis, for the good block where it's possible to perform that analysis of read-retry adjustment. And the block which was found, the address of that block, we can see here. Sometimes, actually, we have not seen that yet, probably, but we suppose that the block may be selected wrongly. There might be some false positive result, and the block may be incorrect. So in that case, you can try to adjust it manually. You can search for the block by yourself and set it here. Okay, so the block is selected. For now, let's just try to use the one which was found automatically. Now let's go item by item here in the instruction. So the first step would be to ensure that the profile is selected, and then you would need to click onto the run. Which profile? So basically it's here, read-retry profile. And normally the profile here has to be selected, should be selected. If it's not selected, if it's empty, can check it. So if it's empty here, then it means that the read-retry either is not supported for that specific chip you have, or we just don't know. I mean, there is a database of read-retries and memory chips. And in that database is written that for that specific chip, this read-retry is good. So read-retry may be supported for some specific chip, but we just did not see that chip before. So that's why we did not specify that much between the chip and read-retry. In that case, it would be empty here if it's not supported or if it's not added to the database. So basically, if you see here the empty field, you would need to make a ticket in our support portal, and we will either try to create the read-retry for you, or we suggest to select some of those read-retries which may be good for the chip, for your chip. But if it's selected, it's you can just go. You can just proceed the next step. So if it's selected, you need to click on the run button. So that's there is only almost one button, only one button here. We need to click on this, and then we need to analyze those graphs. So basically here we are supposed to find the graph which looks like a curve with some quite visible bottom part. So there should be something, you will see how it should look like. So we need to see here a curve, and that curve must have some bottom part. And in that bottom part, the best read-retry values will be located. So basically, on this graph, we have on the vertical axis so-called error score. So if it's higher, then the probability of errors is higher. If it's lower, then it's better. Then the probability of bit errors is lower. And on this axis, we have the read-retry values. So basically, we would need to find some point where with minimal error score, some point with minimal error score. And that point will be applied to this to the reading. Those parameters will be applied. And have a look. For now, we don't see, we don't have we don't have the curve, which clear bottom part. We actually have some mountain here. And it happens because different controllers may use different allocation of read-retries and those curves. The thing is that you have here two graph views, centered and sequential. The centered means that the center of read-retry range is placed to the center. And actually, not the center of it, but the beginning of read-retry, and the beginning and the end of read-retry range is placed to the center. And in most of cases, it's the better, it's correct view for the cases, for the devices. But sometimes, for example, in this Unix device, we don't see the normal curve because the graph and read-retry representations here is better to click to switch to sequential. Basically, have a look. We have here the curve, but the lowest part here is located here in this area. You see that? So it begins from here, goes down to this area, and then proceeds from here. So that's the curve, but it's just not that convenient and clear to see that. So to make it more visible, we can switch it to sequential, and then we can see just a good curve, good line with a clear bottom part. Different memory chips have different thresholds, different number of thresholds, like MLC chips may have 2 thresholds, 2, 3. TLC chips may have 8 thresholds. I will not now go deep in that theory about thresholds and charges in memory chips. The thing is that on this graph, you can see the distribution of error score among according to the read-retries for different thresholds. And here you can switch that numbers, switch the thresholds. So this is the 0, 1, and this is the next threshold. And the idea is to select the value where the line has the read-retry, where the line has minimal value. On threshold 1, it's apparently A5. And as you can see, A5 was placed here automatically. In case of threshold 0, we have many options here. So basically, the first one was taken. I believe you can just zoom it in, and we can see that it's 54, and 54 is here. And that's basically all you need to do here. You need just to run it and make sure that you see something like this. If you see something like this, then you just may not worry about these values, because our utility will automatically take the lowest values from these graphs and place it here. In case if you would have something like described here, the graph is noisy and it doesn't look like a curve, but looks like a horizontal line. So maybe the block address is wrong and you need to find another block address. If you don't see full such a curve, maybe the tuning range is not wide enough, and in that case you can run extended tuning range. So the default one is like the values which are known best for this chip, for these types of chip. But if you, with your specific chip, you don't see such a, like for example, it looks like this. You see the first part of the curve, but you don't have this one. You can run extended range, and then the curve will be, yeah, you see it's much bigger. But apparently the lowest part is actually should be very similar. So it's 54 A5, and with default it would be 55 and again A5. So for this case, where we see the clearly defined the bottom of curve, we may not go, it's not necessary to go for the extended range. But for some other cases, it might be necessary. Yeah, and this topic I already explained to you. If you have something like this, so you don't see, instead of a curve, where you have some hue here, then you can try to switch it to these two options, and then the bottom will appear. Also, you need to pay attention if there will be some false positive drops of the curve. So basically, imagine that we have this curve here, and at some point in this area, we have some drop to this area, and then it goes back here and then proceeds here, like that. So I would suggest you to take one of those values from this bottom, because this one might be just some false positive result, which is better to ignore, because the trend here, you see that actually it's the trend in this area is not the lowest part of the graph. So yeah, that's basically the similar situation like on stock. You need to find the lowest part where you have to buy the stock, and then it will start to grow. Ideal deal. Okay, after you found that it's all good, if it's all right, you can just click on apply and read the chip, and these values will be used to read the memory, and you are supposed to get the good done from the first try. I guess that at this moment we can I can just demonstrate you how good it works actually. Put some timer here. So first of all, let's try to read it without the tuning. So I will click on continue without tuning, and it will read it with a default parameter. So say like it would read before, or like any other tool reads the memory chip without any additional commands. And let's read it for 1 minute, and then compare, and then check the result, how good done we will get. So I will click on console, and let's check the ECC here. So at first it's empty chip. Oh, and have a look. Now, after that, we have only red pages. So it means that the number of bit errors here is so big, so large that ECC cannot correct it. So for this device, it would be necessary for sure to read it again. And after that read with read-retries, of course, the result would be better. But to achieve it, to get it, you would need to read it a second time. So you would lose at least time of one reading. And so here is the data. Let me just check if we have some zeros from the beginning. Trying to find some patterns where we can compare the reading with and without tuning. Not sure that this is the zeros. Okay, maybe there are no any zeros here. Anyways, let's just now remember this. Let me do it like this. I will copy this address, paste it here, and now we can see the ECC map on this specific address. And after that, let me run the reading one more time, but this time already with fine-tuning. So let's run the search. The values pretty same, and this time I click on apply and read the chip. And let's again measure 1.5 minutes. So now it will rewrite the previous data, which was read before in this physical image. And yeah, we will see the data which would appear with fine reading. I guess it's enough. So as you see, I read again that 10% of the memory. We open the physical image, we see that we have some data from the beginning, like first 10%, and then it's just empty. So data has not been read in this area. But most important part is the ECC map. Until now, it's still the read because ECC, there is a file where information about the state of ECC is located. If we want to wipe that file, if we want to clean it, and if once ECC's state was detected for some block or page, it will be written to that file. If we want to check same page, same block again, it would be necessary to click on this button, Clean ECC Map. And now that file, all that previous data was erased. And if I click now, should I do it like this? Disable ECC map and enable. And the address here is the same, I believe. Here, it's the same address. And we can see that fully read dump that was here before now is almost all green. There are still some red pages, but overall, of course, it's much like dramatically smaller number of red pages here than we had before. And with fine-tuning reading, you get such a dump from the very beginning. So it means that you would not need to read it again, because normally when you read some chip, you at first try you get only red dump, then you run reading again, so you read it one more time and spend time for the reading and also for the checking of the data. And when the page is read, it takes much more time to check for the ECC algorithm comparing to the light green page. So the fully read dump would be processed much slower than light green dump. And imagine you have some SSD drive with capacity like 256 gigabytes, for example. If, without this algorithm, you would need to read it at least one more time in order to get close result, which you can get now with a new algorithm. So that's the first case. Now let me show you the next one. So That's case number 2. This time it's a monolithic USB flash drive with Unix memory chip again. So this is the UFD monolith, 16 gigabytes as far as I remember. And yeah, again, we can either scroll this whole list and search for our device, or there is one trick here. We can click on read ID, and the VNR will try to read memory chip identifier from your specific device, and then we'll keep here only the device with the same ID. And because you need device with exactly same ID, of course, it's this is good option, because instead of tens or hundreds devices, now you have only 3. And you need just now to compare your device with the device from the picture. And in my case, I guess this is the one. Yes. So that is the device we have for the analysis. Okay, next. Set configuration. There is only one. Then apply, check reading. Let's check the reading. It seems to be not bad. Let's check the end of the page. Oh. And have a look, this is already not good. This pattern looks like some shifts. So maybe before we even try to read the chip, we would need to adjust a little bit the power. Okay, let's try to do that. So what I can do now, I can change the power on fly for this memory and check if this pattern will disappear. So the default value is 3.3 volts. Let's try 2.5. Oh, and you see, actually it was a part of bad column actually. Let's try to change the voltage again. Oh, and now it's much better. And that's another option how you can improve the quality of the dump. You can change the power and on fly control the quality of the dump. All right, so the power is adjusted. Now just go to read memory chip, one chip, solution, apply. Everything is same like it was before. And this time we have read-retry 4, which has already 1, 2, 3, 4, 5, 6 thresholds. And let's run the analysis. And yeah, again, we would need to switch here the centered view to the sequential. See, in case of sequential, we have quite a nice curve here. Oh, and this time, have a look. This curve is not kind of finished. We can see that the bottom is here, but maybe, and most probably it's actually the lowest part of the curve. but we can try to make it more full. So the same as here, it's not full. Here is the full one, again not full, and here is not full also. So what we do, we switch to extended range, click run. Yeah, and now the curve looks like this. So now it's the full. Here like this and like that. So now it's all good. But again, let's first try to read it without the tuning. Forgot to do this second time. Continue without tuning, and let's wait 1 minute. All right, so 1 minute is enough. And I actually see that we cannot check the ECC because there are bad columns here. So if we try to check the ECC, it would not work anyways. So firstly, we would need to search for bad columns, but I think with our automatic bad column selection, it would be really quick. So here we have the bad columns, which look like such FF bytes. I guess that universal algorithm we can apply. Yes, universal algorithm makes some false positive suggestion that this is the bad column, but it's actually the service area. So what we can do, we can click on uncheck all of this type, and FFs are actually the ones we would want to select. Yeah, so we can do check all of this type, and yeah, now all these bad columns are checked. So add all bad columns, 126. And the same let's do for the second plane. Auto detection. This is not bad column. You see, this is a universal algorithm, so it can do false assumptions. So we would need to adjust it and check all this type and check all. So all effects are checked. Wait, okay, and bad column 128. Okay, so I hope that it was done correctly. Let me just, I guess I can do it here. Let me check if all the structures are located on corresponding position. So service area. So it's all correct. So you just have seen that I selected around 250 bad columns within 1 minute, maybe 2 minutes. Another great thing about visual NAND reconstructor. So the bad columns are selected, and now the ECC will show some correct results. And as we can see, the results here, again, not good at all. Almost all green, or sorry, red, and just only some pages are, oh, let's pay attention on this block. This is the block with zeros, and all these dots here belong to the bit errors. So let's remember this address. All right. And yeah, that's the address we have here. Let's do a screenshot, and later we will compare it. Screenshot did not appear. It's pasted here then. All right, so we got screenshot. And now let's run the reading again, but this time already with fine-tuning. So run. Let's run extended search just in case. And apply and read the chips. Okay, that's enough. And let's see. The ECC, clean the map, close it, open, and here we go. It's all light green. Let's open the same block, and now you can compare it. How did it look before, and how does it look now? So here is the default reading, and this is the reading with adjustment, with fine-tuning. Okay, that was the next impressive example. Now let's move on to the next one. We have the last one actually. Okay, the next one is actually one of our favorite ones. This case is the Western Digital green SSD drive. All right, so this is the SSD drive. Let me select the SSD, 120 gigabytes, and the controller is SanDisk, which has these numbers in the name. So it's 20, 82, 00, and so on. And finish. Okay, set configuration, all the already known steps for you. Apply configuration, check reading. The reading is fine, I hope. So here we got SLC pages. Not ideal ones, but okay. Read memory chips. This SSD drive has 4 memory chips. The solution is located in database, so we can apply it. That's the solution, and now let's read the chip. Okay, this time I will not try to run it and do the things. I will just continue without tuning and read it for some time. Again for 1 minute. Okay, so we are close to the end. You see this chip has much larger capacity, so within 1 minute it has only 1% read. Okay, so the data is here, as you can see, and then the dump is just empty. Let's check the ECC. So these green areas green pages belong to SLC blocks. If we open it, we'll see this SLC blocks. The blocks with data not gonna be so beautiful. Let me scroll it a little. Yeah, here it would not be that simple to find the block. Okay, maybe let me try to do it here. Oh, you know what? Let's run reading again and check the block. Yeah, which it finds automatically. So this block is supposed to be the block with data. Now let's go to the ACC, place this value here, and that's the data. You see one single block with data. Actually, all the data begins a little bit later. And now if I put the same value here, we can see that this block is actually fully read. So full block has only bad pages. After that block, I guess we will have again, yeah, empty block, because that block is surrounded by empty blocks. And if we, as usually, just run the reading, and this time with read-retry with fine-tuning, it should be better, much better. Okay, so for this SanDisk device, the graph looks like this. First threshold, yeah, second. So basically, we can see here quite nice bottom part. Here again. So overall, it's totally okay. I think if we run extended search, it will be more or less the same. Well, actually, no, it's more full now. But the lowest part allocated approximately on the same areas. Apply and read the chip. One minute timer. Okay, so that's enough. And if we now try to read the same address, which we analyzed before, and as remember, it was fully red. Now it's almost all green. There are still some red pages, which will be fixed on next read, but imagine that like if all these pages would be red, VNR doesn't know in advance if it's red or not. So VNR will check each page from the very beginning. And if it's red, it will see that it's the red. It will try to read that page again with read-retry already. And then the next page will be checked and will be read again, the next one and the next one. So it's like a lot of reading commands will be sent, a lot of reading attempts. And if you have such dump initially, so VNR will only try to read again this page, this one, this one, this one, instead of all of them. So the process will be much faster a lot. So I believe, guys, you understood. You got the point that now you will get much better dumps. Now it works much better. You don't have to do any additional specific things. All you need to do, just click on read memory chips, and then algorithm will do all the things for you. You only need to make sure that you have here normal curves, normal graphs with clear bottom parts. And once you see that, you just click on apply and proceed the reading. That's the visual NAND reconstructor number 11. Thank you very much and see you later. Bye.